Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about what we do when gases aren't quite so ideal. So these are infamously known as real gases. And so one of the ways we can go ahead and talk about real gases is by starting with a simple equation. And this is a trick that scientists love to use. If you have a system where you have a good equation that just tends to fail for known reasons, what you can do is try and modify this equations by knowing how to correct for each of those failures. So the ideal gas law had two major failing points. One, it assumed no attractive forces, and two, it assumed that the gas didn't actually occupy any volume. So the easiest one of these to address is that real gases occupy real volume. So all we need to do is into our ideal gas law, essentially account for the fact that not all of this space is usable. So the only available space for gas molecules to move around is going to be that total volume minus whatever volume isn't occupied by a gas. So we need to know the amount of gas present, and we need to know exactly how much volume is going to be occupied by 1 mole of the gas. And so we introduce what we call the B parameter. And so this is literally going to be the volume occupied by 1 mole of whatever gas I'm working with. However, this introduces a very important point of a deviation from the ideal gas law. The ideal gas law works for any gas. Identity doesn't matter. However, once we get to this first modification, now every gas occupies a different volume. So the B parameter for hydrogen will be much smaller than the B parameter for, say, chlorine, because it turns out Cl2 is a lot bigger than H2 for some reason. And so this addresses the fact that every gas is going to behave a little bit differently, especially under these extreme circumstances. However, it does end up producing a much more all-encompassing equation. So now our pressure times our available volume will equal nRT. So we do start to see a concentration dependence here on the left side of the equation. However, we also need to work with the attractive molecular forces. And we can do this by first rearranging our equation to look at pressure. Because it turns out that as I introduce molecular forces, I'm going to see a modification over the pressure felt by the walls of the container. Most specifically, the pressure felt by an external object is going to be reduced by however much the two gas molecules tend to attract each other. So the more attractive the force, the less of that speed and movement is going to end up hitting the wall of the container. So we're going to introduce a new parameter, which again will be dependent upon the identity of the gas we're working with, called the A parameter. And it's also going to be modified by the likelihood of our gas molecules occurring. So the higher the concentration, the more likely I'm going to watch two gas molecules hit. However, it takes two to tango, so we're going to have to multiply the concentration of the gas times the concentration of the gas. So we're going to square the concentration and multiply it by the attractive force, and then it will reduce the pressure of the system by that much. However, in order to make our van der Waals equation look fairly similar to the ideal gas law, we're going to add this A times the square of the concentration to both sides, and then multiply by our available volume to get our full van der Waals equation as you'll typically see it. And one of the things I like to emphasize with van der Waals is you can back out each piece of the equation simply by knowing how a system behaves. So again, now we can go ahead and figure out what the real measured pressure is related to the actual volume of the container, essentially correcting for those approximations we made with an ideal gas. However, the amount of gas and the temperature will just be however much gas you put in and the temperature of the system. So next time, we're going to be taking everything we've learned about gases and trying to apply it to real chemical reactions and real chemical systems. Until then, take care.